Okay, in this video we're going to talk all about maximums and minimums and things you would need to know about those for the AP Calculus exam. This is also a really good review if you're in Calc 1 or 2 in college or anywhere. So let's kind of get started and see. So we want to talk about relative or local maximums and minimums. That's one idea, relative, versus the idea of an absolute or a global maximum or minimum. You really don't use the word global in AP Calculus, but it's another word for it. So what does that look like? Well, if we have a picture of a function, then there are some places where there are relative maximums and minimums. So that would be these 3 points. So you have a relative minimum, then a relative maximum, then a relative minimum. So these are your relative maximums and minimums. Now you also will have your absolute maximums and minimums, and those are like literally the biggest it will ever be and the smallest it will ever be. So you can see one of them, that first local relative minimum, is also the lowest the curve will ever go. That is actually both. So these are absolute. One of them is an endpoint. That can definitely happen. You can never have a relative max or min at an endpoint, but you could if a relative max or min is the actual biggest or smallest. One of them could end up both, or two of them could end up both. So that's what we're talking about. And let's go through some of the things about each of them. And I'm also going to show some work. I didn't really do any problems, but I did work. You'll see what I mean as we go. So let's talk all about relative maximums and minimums. First of all, they must occur in an open interval. So they cannot be an endpoint. That's one of the first things that you definitely have to get into your head. So relative or local maximums and minimums will always be in an interval. So you're going to see the curve change from increasing to decreasing or decreasing to increasing. It's not going to be an endpoint where suddenly the curve appears. So these things will occur at critical points. So you have to know the definition of critical points. So critical points are where f prime of x equals 0 or f prime of x does not exist, but they have to be in the domain of f of x. So if f of x has a vertical asymptote, the derivative is not going to exist there, but since that's not in the domain, you don't get a critical point. So it has to be in the domain of the function, and then the derivative is 0 or the derivative doesn't exist. Another really important idea is that not all critical points are going to be relative maximums or minimums. We're going to have to figure out if it's a maximum or a minimum. Now, sometimes people wonder, like, how do I know if I'm supposed to be finding a relative max-min or an absolute max-min? Well, going through like every AP exam, I spent a lot of time on this, going through basically every AP exam, I can say somewhat confidently, though not 100% confidently, questions pretty much always will say relative or local maximum or minimum when they're asking about relative maximums or minimums. That you could contrast that with when they're asking for an absolute max or min. Sometimes they say absolute, sometimes they don't. But if they're talking about a relative or a local max or min, they will say it. Also, relative max or min seems to be more the the preferred nomenclature these days. When I looked up, I just did like a search. The use of local kind of went out of favor in like 2005, I think. And then from 2005 on, basically it's always called a relative maximum or minimum. So that's kind of the terminology thing. What we need to know is we definitely are going to need to know how to justify our conclusions, because we're going to be asked, like, where is there a local max or min? Justify it. So let's go through the options that we have for that. So the first one is, I think, probably the most common way to do this, and it's the first derivative test for relative maximums and minimums. So I think it's important or useful to always say the first derivative test for local or relative maximums and minimums so that it's in your head linking the two ideas. Here's what it basically says. So if x equals c is a critical point of a function, so that means it's a point in the domain of the function and the derivative is either 0 or undefined at that value. But if x equals c is a critical point and f prime changes from positive to negative at x equals c, then f of x has a relative maximum at x equals c. That's the first part of the first derivative test. So let me just show you what like work might look like for that idea. So what I usually do on these, however you go about it, you have to figure out the derivative, or maybe you're given the graph of the derivative, but you need to be able to look at it and you need to be able to at least visualize or actually draw a sign chart. So I have drawn a sign chart for f prime where the critical point is at x equals 3, but for some reason I'm about to use 2 accidentally. So at x equals 3, this cannot be our justification. Our justification needs to be words. So I've shown that the derivative is changing from positive to negative at x equals 3, and I'm about to describe it at x equals 2 for some reason. Actually, this is kind of a total mess. Hold on, let me, all right, I'm gonna show it. Actually, you know what I'll do here? I'm gonna just change this 3 into a 2 somehow, but hold on, I gotta work out how to do this. You're gonna be a 2. I messed this up twice. Okay, 2. Here we go. Now, here is my justification. Since f prime changes from positive to negative at x equals 2, f of x has a relative maximum at x equals 2. That's it. That's what we mean when we say justification. So you can make a sign chart, but that does not count as your justification. No one's going to look at that and say like, oh, they know what they're doing. You have to translate it into words. I don't know. It's an emphasis. All right, the next thing we're going to do. So that's a critical point where the derivative changes positive to negative. So you could have a critical point where the derivative changes from negative to positive. That would mean that f of x has a relative minimum at x equals c. So let's take a look at some sample work. So I made this one a little more complicated, and then I messed it up. So let's see. F prime, I'm showing that f prime is going from positive to negative at x equals 3, which would be a relative maximum, and then also from negative to positive at x equals 5, which would be a relative minimum. So this is the work. This is not justification. Now what we do is we write down our words for justifications. So I'm going to say, here you can see I messed up. I just use a generic value of c. What am I even doing? Since f prime changes from negative to positive at x equals, look, I did it everywhere, x equals 5. Let's get rid of this. Let's get rid of this. Let's change this to 5 and 5. There we go. So since f prime changes from negative to positive at x equals 5, f of x has a relative minimum at x equals 5. This is our justification. So that's the kind of thing you're going to find yourself writing often. I think this is the most common way to justify a relative maximum or minimum. You should also know it is definitely possible that f prime doesn't change sign at x equals c. That just means that there's not a relative maximum or minimum at x equals c, and for whatever reason, f prime decided to be either 0 or undefined. It doesn't really matter because that's not what we're trying to classify. It might be a point of inflection that happens frequently, but it also might not be. So if we're just looking for maximums and minimums, that's kind of like a non-event. All right, another thing we could use, so that's our first derivative test for relative maximums and minimums. We could use the second derivative test for relative maximums and minimums. So here's what that says. It's 2 parts. It says, if f prime of c equals 0, so equals 0, this is big. You can't have a critical point where the derivative doesn't exist. That will not work here, because if the first derivative doesn't exist, the second derivative cannot exist. But if f prime of c is 0 and f double prime of c is greater than 0, then f of x has a relative minimum at x equals c. So let me show you like some sample work. So this is important. The f prime of c equals 0. Got to be true. Sample work, here we go. I'm just going to say if f prime of 3 is equal to 0 and f double prime of 3 is 12, right? So somehow you figured this out. Maybe use a calculator. Maybe you had to compute the derivative and evaluate it. I don't know. Anyway, you actually know, or maybe it was given in the problem. So what I like to do on this is I like to actually just draw. Like I'll draw a horizontal line to represent f prime being 0. And then concave up, I will just draw something concave up. So I am drawing this to be sure that I make the right conclusion. The conclusion here will be, since f prime of 3 is 0 and f double prime of 3 is greater than 0, it doesn't really matter what it is as long as it's greater than 0, f of x has a relative minimum at x equals 3. And I could see it in the picture. That's why I'm drawing it. So this is my justification. People would be happy with that. Now the other option would be, if f prime of c equals 0 and f double prime of c is less than 0, that would mean that f of x has a relative maximum at x equals c. And the work looks basically the same. So our work, I made it up again. F prime of 2 is 0, and f double prime of 2 is negative, right? Negative 5, but again, it doesn't matter as long as it's less than 0. Here's my picture that I'm going to draw just to make sure I don't, know what I'm doing but say the wrong thing, which actually happens to me a lot. So I'm better off if I draw a picture. So here would be my justification. And notice this one's a little bit different. So I'm saying since f prime of 2 is 0 and f double prime of 2 is less than 0, f of x has a relative maximum at x equals 2 by the second derivative test. So here I decided to say that I use the second derivative test. Is that necessary? I don't think it's always necessary. Actually, I don't think it's necessary at all. But to be really careful, you should probably do it. So this is justification. And just to highlight the difference, on the second one, I specified that I use the second derivative test. On the first one, I did not. When you use the first derivative test, you basically never say that you use the first derivative test, like a secret. We all know that we're using it, but instead we just state why there's a relative max or min. Second derivative test, kind of the same. So you could do the first thing, but some people are more comfortable because this seems more involved, actually saying that they're using the second derivative test. I am here to tell you it doesn't matter. You don't have to say it. You could not, whatever. All right, so let's talk about when we're going to use each of these. So the first derivative test, or actually, I put this little like subtitle here. Just do a lot of problems. If you do enough problems, eventually you will get used to it and you'll look at it and be like, oh, first derivative, for sure. Second derivative test, for sure. But these are, to me, like places where I would think to use them. And looking at, I looked at every FRQ since 1998, and these are the places where I would choose to use one or the other of them. So if you can easily make a sign chart for f prime, definitely use the first derivative test. There's no reason not to. So that's if you can easily do that. Sometimes you can't, or sometimes you don't have enough information. But if you can easily do it, definitely do it. If you're given a graph of the first derivative, which is by far the most common type of graph you will be given, you can use that as a visual representation of a sign chart, right? Anywhere f prime is positive, your sign chart would just have pluses. And anywhere your first derivative is negative, your sign chart would just have negatives. So it's actually a picture of a sign chart. So that's where you're going to use the first derivative test for sure. If you have a calculator and your calculator can graph f prime, obviously you're in the same sort of scenario. And then if you just have enough info, like you might have a table of values that's very specific and it's telling you like, all the critical points and telling you some of the values in between. You'll know it when you see it if you do enough of them, but if you have enough information, first derivative test for sure. Second derivative test, I find my students are less likely to want to use, even though when it is applicable, it is by far the best way to do a problem. So for example, you might use it if you have f double prime or you can find it easily. If you can't find f double prime easily, you might not want to get involved with the second derivative test unless the sign chart is super hard to make for f prime. Then even if the second derivative is challenging, you might want to go for it. Another place is if you're doing a problem involving differential equations, right? So if you are given dy dx is 3x plus 2y minus 5, how are you making a sign chart for that? I have no idea. Like given n ordered pair, what does my sign chart even look like? You basically can't do it, but you could find the second derivative and evaluate the second derivative at the point, and then you will know if you have a max or a min. If you can let your calculator do the work, your calculator doesn't mind finding second derivatives, even if they're incredibly gross. So you could definitely do that. If you're given info that allows or even forces you to use it. So sometimes they just tell you that f prime of 6 is 0, f double prime of 6 is positive. What can you conclude? So that's definitely a thing. And then if you are in Calc BC, you're going to use this on Taylor series and Taylor polynomials all the time. You basically give up the idea of doing a sign chart and you just embrace the second derivative test. So those are places that you're going to be using these. I kind of forgot to write down and mention this, but I should mention sometimes when they ask you if a function has a maximum, a minimum, or neither at a critical point, sometimes the answer is actually neither, right? You will try to evaluate the first derivative at that point and you won't get 0 or undefined. You'll just get f prime of 10 is 53. That means there isn't a max or a min, so the answer there would be neither. So don't be afraid when you get neither. They actually do that. It seems like they wouldn't, but they do. All right, so moving on from that, let's talk about an absolute max or min. So these could also be called global, but not in AP Calculus. They call them that in like Calc 3 is where that really becomes a thing. So absolute maximums or minimums. These can occur at an endpoint or a critical point. So if you go back in the video to that first picture that I drew, one of the absolute maximum was actually at the endpoint. So they could happen at an endpoint or at a critical point. For these types of problems, the question might not say absolute. It might just say, find the maximum or the minimum on an interval. So when you're dealing with an interval, you basically know immediately well, no, you don't know that. When it says absolute is when you're looking for this. Or more specifically, when it says relative, you know you're looking for relative. If it doesn't say relative, you're looking for absolute. That would be my encapsulation of that, I guess. So some of the words they say, like, they won't say necessarily absolute, max, or min. They might just say, like, find the most, or the least, or the farthest left, the farthest right. Things like that. Things that are, like, showing biggest or smallest. That's when you're doing absolute, max, or min. So these will almost always involve an accumulation function. So an accumulation function is awesome. So you can write accumulation functions. They're just functions that have integrals in them. So they look like this. F of x is basically f of a, the amount you're starting with, plus the integral from a to x of g of t dt, where g is the rate of change, right? So what that means, by second fundamental theorem, is that f prime of x is g of x. G of x is the derivative of f of x. So that's usually the setup. Usually you actually have a graph, actually, of g or of f prime, and you do the problem based on that. So another thing is, pay attention to what you're asked for. So some questions will ask you for the maximum or minimum value. Others will ask you the time at which the maximum or minimum value occurs. And paying attention to that can save you a lot of hassle and trouble. And also, sometimes it's impossible to find the value of the function. All you can find is the x value or the time. So definitely read the problem and see, am I being asked for the y value or the x value? You have to know that going into it. But we do need to be able to justify our conclusions. So how are we going to do that? Well, we have two options here as well. So for relative max and mins, we have first derivative test, second derivative test. For absolute maximums and minimums, we have the candidates test, which is one of my favorite things in calc to do. So the candidates test says, if f of x is continuous on the closed interval AB, then the absolute maximum or minimum of f of x occurs at an endpoint or a critical point. That's all it says, but it does a ton of work. So here's some sample work for you, basically. I'm going to say that the endpoints are 1 and 5, so let's say we just read those from the problem. We look for the critical points. We see f prime is 0 at 2 and 4. We also notice that f prime doesn't exist at 3. Make sure you look for where f prime doesn't exist. People ignore that frequently, and often because the people making the test know you're going to ignore it, that's where it will happen. So we got to look for where f prime is 0, where f prime does not exist. I'm going to just say that f of x is 5 plus the integral from 0 to x of g of t dt. That's fine. Like, you would read the problem and write your accumulation function. What you're going to do now is you're going to make a table. You're going to do this every time. You're going to make a table. It's going to have the x values you're interested in, and then the function values at those x values. So at 1, I'm going to get y1, 2, I'm going to get y2, etc. And then I'm just, for the sake of argument here, I'm saying that y1 is the absolute biggest number in that list of y values, and that y3 is the smallest number in that list of y values. That's important. In this table, you are definitely looking at the absolute maximum and the absolute minimum y values, so that you know confidently that whatever's biggest is the absolute max, whatever smallest is the absolute min. So here's what my justification would look like. It's a lot of writing, but you should do it a lot so that you are just like muscle memory getting through it. So here we go. F of x is continuous on the interval from 1 to 5. That's what makes you allowed to use the candidates test. Then you say, therefore, by the candidates test, the absolute max or min is at an endpoint or a critical point. I decided to list them here. Sometimes you don't see that, sometimes you do. There are trickier things you can do. You can say, if you're looking for an absolute maximum, then that's going to occur at an endpoint or a critical point where the derivative changes from positive to negative. If you're looking for the absolute minimum, that'll be at an endpoint or a critical point where the derivative changes from negative to positive. I usually just check all of them because there's no real harm in that. And often you usually need to kind of like integrate past all of them to figure out values anyway. So it helps you like organize your thoughts. But that is like an advanced technique of justifications if you're kind of looking for that. All right, so after I write those down, I will just say the absolute maximum is y1, and it occurs at x equals 1. And the absolute minimum is y3, and it occurs at x equals 3. So notice what I'm doing there. I'm giving the value, and I'm saying where it happens. If I can do that, I will always do that, because that way, if I read the question wrong, I still will have answered the question, right? If the question was, what is the absolute max? The answer is y1. If the question is, for what value of x does the function achieve its absolute maximum? The answer is x equals 1. But if I didn't write one of those, I would have been wrong if I wrote the wrong one, so I'm just going to write both. So if I can, I will write both. And then this is actually going to be a part of almost every rate in, rate out problem, and I have a whole separate video on all of those that I definitely recommend. And it's also going to be a part of most of the given a graph of the first derivative analysis type problems. So this is a really important idea. You definitely need to master it. The candidates test is a big deal. All right, there's another idea, but first I want to just touch on something that's related to this, but a little bit different. It sounds like I'm doing an ad, but I'm not. So as an interlude, I would like to just explain the extreme value theorem to you, because I apparently don't talk about it enough in class. And then when we start reviewing, there's always questions and people aren't 100% sure why something is true. So the extreme value theorem says if a function is continuous on the closed interval from a to b, then the function has an absolute max min on the closed interval from a to b. It's basically the engine that makes the candidates test run, right? If the extreme value theorem didn't exist, the candidates test, we would be like, but why does the continuity mean that this is going to happen? In this case, the extreme value theorem is what tells us that. So one thing to look out for, in particular, for multiple choice questions, ask this a lot. If a function is not continuous, then it is possible it doesn't have a max or a minimum. So we kind of know that intuitively from vertical asymptotes, right? Function's not continuous and has a vertical asymptote, you're not going to get a max or a min. There's a trickier graph that you can draw, though, where the function is defined for all values. So let me draw that. So this function is defined for all of the values shown, but it does not have a maximum because of that open circle at the top. You can get as close as you want. The limit from the left will exist, but you're never going to get there. So there actually is no maximum. That's the tricky one where it's defined everywhere. The less tricky scenario is a vertical asymptote where obviously there's no max or min because you're just going up to infinity and down to negative infinity. So I just wanted to touch on that because that does come up and it's related to the candidates test. And really it's the thing that makes the candidates test work. So let's talk about, that's candidates test for absolute max and min. There's another thing you can do. It doesn't really have a name, but I have given it a name. And that is the lonely critical point theorem. So you can see there's like a footnote here. This is the lonely critical point theorem. I also think it's probably supposed to be called the only critical point theorem, but I think it's more poetic and I misheard it the first time as the lonely critical point theorem. So this is not really its name. It actually doesn't have a name, which is a shame because you use it a lot. So you can think that this is the name. You lock it into your brain using this, but don't call it that when you're using a justification. All right, so here's what it says. If a continuous function only has one critical point on the closed interval from a to b and has a relative maximum or minimum at that critical point, that should say then the function has absolute maximum or minimum at that point. Somehow I just messed up writing that. So it should say at that point or there, or there. So what would this look like? So this is a big deal and you can think it through. Like if there's only one critical point, there's only one place that the function can turn around, either from increasing to decreasing or decreasing to increasing. So if you're at a maximum, you can never turn around and get higher than that. So that must be the absolute max. If you're at a minimum, you can never turn around to get lower than that. So it must be the absolute minimum. Here's some work. So f prime of x equals 0 gives me only x equals 5. I'm going to pretend that my interval is from 0 to 8. F prime goes positive to negative. So here's what I would write. It's kind of a lot, but it does the job. F of x has a relative, so I'm basically doing the first derivative test, has a relative maximum at x equals 5 because f prime changes positive to negative there. Now, here's the key. Since x equals 5 is the only critical point on 0, 8, f has absolute maximum at x equals 5. So that's my justification. I'm saying there's only one critical point. At that critical point, I get a relative maximum. It must be the absolute maximum. You could also have gotten a relative minimum, and then at that point, it would be the absolute minimum. So on some questions, you will get a relative max. So say on this question, you get a relative maximum at 5. So that's the absolute maximum. But if the question asks you for the absolute minimum, you now know that that's occurring at one of the endpoints because it's not occurring at the critical point. So this idea is really important and will save you a lot of time. And every time it's on the free response questions, I get a lot of comments on the video of people saying like, don't you need to know the value? It depends on the question. So this will work really well when you don't need to know, when you don't know the initial amount. So you can't really write an accumulation function, right? Like at t equals 0, there's 1,000. We just don't know that. So if we don't know the initial amount, or if we only care about the x value or the time, this is the way to go because you don't have to find the value associated with it. You just find the critical point and you can classify the critical point using this theorem. A really good example of this, the most recent one, is 2019, number 1, part C. People did not like that I did not find the value, but we didn't know the value to start with. So all we could find was really the displacement in fish, whatever that means. Okay, so let's talk about one more thing and then I'll wrap it up, I think. So finding the range of a function, in my mind, is actually a secret maximum, minimum, and limit problem. So sometimes you're asked to find the range of a function. So here's how we can handle that, or the logic behind it. If a function is continuous, you can find the range by considering the function's values at the relative maximums and minimums, and the limit as you approach infinity and the limit as you approach negative infinity. It basically covers all the bases, right? Maybe you have a relative and an absolute maximum at a particular value. Well, you'd still need to know the limits at infinity and negative infinity to know what's going on. Like, do you go down to negative infinity? Who knows? So here's what some sample work would look like. I have a critical point. I have 2 critical points at -2 and 6. Why are they critical points? I'm just making up a problem. It's fine. I do a sign chart, and I can see that f prime is going from positive to negative at -2, so that's a maximum, and then negative to positive at 6, so that's going to be a minimum. So I'm just going to make up values for those. So f of -2 is 10, and f of 6 is 4. Now I still need to know the limits to infinity and negative infinity, so I'm just going to make those up too. The limit as x approaches negative infinity is 7. The limit as x approaches positive infinity is 13. Okay, so what does that mean? That means if you look at it, 4 has to be the absolute minimum. So if you think about it, it has to do with the combination of we know the relative maximums and minimums, and we know the limits. So we can actually draw a picture. We also, for similar reasons, know that the maximum value is approaching 13, but is not necessarily 13. So based on this information, I would say the range of my function is from 4 inclusive to 13 not inclusive, and I think the graph could look like this. Right? So you can see the limit to negative infinity is 7. The relative maximum is 10, so we go up from 7. Then we go down to our relative minimum at 4, but then because of the sign chart, we increase forever after that. There are no more critical points, but the limit is 13, so it does level off. So we definitely know we go down to 4, but we can never go below 4 because of the limit to negative infinity. And we go up toward 13. We don't really know if we hit 13 or not. I'm going to say it's an open interval here because we just don't have enough information. So that's a secret maximum problem, I think. And for example, this is a super old problem, but like there's no reason they couldn't ask about this again. 1998 2C is like the classic example that I think of when I think of it. There are a lot of older problems than that. There aren't really any newer problems, but again, everything old is new again, so you never know. All right, so what I'm gonna do now is show you, I regretted doing this kind of instantly. Here are some problems you could check out. So I'm not gonna read those, just screenshot it. I was like, oh, I'll just write down all of the parts of all the FRQs where you had to do this. It turns out you have to do this multiple times per AP exam on any given thing. So there wasn't a single year that didn't have at least one of them. Most years had at least 2. You can see some years had more, like 2007B. There's 4 parts that are basically asking you for max, min, absolute max, absolute min. It's so common a thing. You just got to master it. But anyway, that's like a huge summary of it. I hope you found this helpful, and good luck.